All righty. So this is going to be chapter 2 for Cutnell and Johnson. So let me go ahead. Chapter 2, which is going to be Kinematics and one dimension. All right. So let's start by talking about motion. What is the definition of motion? Now, we said an object in motion if an object moves. What does that mean? So let's go ahead and write this down. An object in motion when it moves. So what does that mean? When you talk about the word move, that means when the object changes its position. Awesome. So what does that mean when an object changes its position? It means that the object was at one point, the object was at one point, I'll say in space, at one point in time, and becomes in another space at another point of time. So when we talk about motion, we're talking the object when it moves. When the object moves, it means changes its position. That means it was at one point in space, at one point of time, it becomes a different point of space and a different point of time. And that's what brings us in to our kinematics in one direction. That's what we just defined. We define the motion. We say an object, the object moves if the object changes its position. That is, the object is at one point in space and one instant of time, and a different point of space and a different point of time. Now, usually when, I don't know about you, but me, when I actually move or travel, I usually like to take my car. All right, now, once we define motion, now how do you usually move? Now, usually when I go to work or, or to school or whatever, I usually take my car. Which if you call me and ask me what the average speed that I go in, usually I tell you, I don't know, usually I go about on the highway about 65 miles per hour. Well, actually, we can write it like that. We can actually go ahead like 65 miles per hour. Some people go 70 miles per hour. Now, when you actually talk about the speed that I'm going to, and let me actually go back to 70 miles per hour, 65 miles per hour, we're talking about what? We're talking about miles per hour. What is miles? Where miles is another fancy word for, you guessed it, distance. And what is hours? Hours, when you talk about hours, It's another word for time. So really, when you're talking about apparently my computer crashed, so let me go ahead and write this again. So hour is another word, fancy word for time. So really, we're going 65 with a unit of distance over unit of time. And what we're talking about the speed. So your speed, which is 65 distance over time, which is miles per hour, that's what we define as your speed. So really, we can say your speed is your measure of your distance over the rate which you move over time. Now, we will give this speed a variable letter V for velocity. So we got another word for speed, which is your velocity. We're going to give it a V. Your distance, we're going to give it a variable D. And your time, we're going to give it a variable T. So basically, your V equals your D over your T. Your speed equals your distance over your time. So for example, if I tell you you were going, let's say 60 miles, you went 60 miles in 2 hours, what is your speed? So, okay, so it'd be 60 divided by 2. So basically you'll be talking about your 30 miles per hour. That's your average speed. Or let's say, let's do another example. Let's say you went, let's say you went really fast. Let's say you went 24 miles in 1/2 an hour, 0.5 hours. That means your speed in this case would be what? Well, 0.45 divided by 1/2. So you're talking about your 48 miles per hour, which is, again, we're talking about your distance over your time. Now, the average speed that you're traveling is the total distance traveled by the object traveled by the divided by the time taken to travel that distance. So your average speed is your total distance traveled divided by the time taken to get there. Which is, again, your distance over your time. Now, if you're traveling down the highway and I call you and I say, what is your speed that you're going in? Let's say you're going in, if I call you, like this is right now, this is me over here. And I come in and here's my cell phone. And I call you while you're driving your car. And here you go, you're over here driving the car, going in. And you answer the phone call and you're saying, well, I am going at a speed of 65 miles per hour. That is your instantaneous speed. That means you're not going 65 miles per hour the whole time. You're at that point when I call, you are going 65 miles per hour. So to go ahead, again, your motion is defined as if the object changes the position, which means you are at one point of space at one instant of time, and a different point of space in a different instant of time. Now, the speed of a moving object is the rate which covers the distance. So your speed that you're actually going to is your distance over your time. And the best thing, the best example is when you actually go drive your car down the road. So for instance, if you're going again 60 miles in 2 hours, we define the speed as 30 miles per hour. When we went 24 miles for half an hour, we looked at the speed and we calculated to be 48 miles per hour. Now, the average speed is the total distance traveled by the object divided by the time taken to travel that distance. Where instantaneous speed is the object speed at that given point of time. Okay, now let's go ahead and look at our first video, which is your air track 1.
We'll float this glider on a cushion of air.
Precision. I don't know why this video cuts off always so short, but so you got a glider that's going down and we're taking it every 30 minutes, the position of the glider. What does those dots tell you about the glider's precision? Is it slowing down, speeding up, moving at a constant speed, or any of the above? Go ahead and lock in your answer right now. And let's go ahead and look at the next video.
Since the spacing between dots is
So the spacing between the glider stays the same. Now, notice in that video saying the speed is the same, but the velocity, it depends on the direction. And that's when we actually want to talk about something called a scalar and a vector product. Now, there are two types. Let me go ahead back to my notes. Now, we have two types of physical quantities. You get your scalar and you get your vector. Now, a scalar quantity, direction does not matter. With the vector, the direction matters. So going back to our example, or if you're driving down the road and I give you a call and it's like, how fast are you going? You say, I'm going 65 miles per hour, right? This one is your scalar, which tells you what was the speed, or in case, instantaneous speed. Now, your velocity matters whether it goes this way or whether you deaccelerate and you go the other way. So the direction matters. So notice that I put an arrow where the velocity is. Let me actually go ahead and write that down. Have an arrow on the velocity. This arrow indicates that it's a vector quantity. So with your vector, the direction matters. With your scalar, the direction does not matter. Hence, you got your speed and your velocity, and that's the difference between your speed and velocity. For this one, the speed, we're just talking about instantaneous speed. We don't care about direction. With the velocity, we're talking about your average velocity, and the direction matters because your velocity is a vector quantity. It matters. And this one is a scalar. So your velocity equals your distance over your time. This is your distance. This is your time. Velocity. Now, if we cross multiply and we solve for the distance, so your V equals your D over T. That means if you solve for your distance is going to equal your velocity times your time. If you solve for your time, that means well, let me actually get a different color for that one. So for your time is going to equal how much distance divided by your velocity. So let's say we got a question going on. Let me go ahead and save this. How far does a car travel in 4 hours at a speed of 40 miles per hour? Now, I would like to take this opportunity to introduce my 4 wonderful rules, and this is going to be called Dr. Malek 4 rules. And if you ever watch Marvel, let me go ahead and put a circle, which means that's going to be my 4 fantastic rules. Yeah, Marvel Fantastic 4 rules. So your rule number 1 is you're going to write down the info. Rule number 2, is going to be something is going to equal to our double question mark. Number 3 is going to write down the equation. And number 4, like plug and play, this is going to be called plug and solve. So every time we're going to work on solving problems, moving on forward, you're going to be using those 4 fantastic rules to make your life a little easier. So let's go ahead and see what's going on. We got this: how far does a car travel in 6 hours at a speed of 40 miles per hour? Now, our first rule is we write down the info. The way we do that is by looking at the numbers. So the first number we have is your 6 hours. That's 6 hours. You're talking about hours. You look at the unit first. The unit tells you what that number is. Now, when you talk about the unit, you're talking about hours. Hours tells you is going to be what? Time. And you got 40 miles per hour. That's distance over time. You know, distance over time, that's your velocity. So your time, in this case, and this is going to be example 2.1, Your time in this case can be 6 hours, and your velocity is 40 miles per hour. A mile per hours. Now, is there any other numbers? No, there is not. So that satisfies rule number one. Rule number two is something equal to double question mark. That is very important. You need to know what you're looking for in the question. Now, what are we looking for? How far? We're talking about how far does the car travel? That means we're looking for what? For our distance. So coming back over here, we can define our distance as what we're looking for. That's our double question mark. The third rule is write down the equation. Our equation is, our main equation is, and let me go ahead and write this down for number 3, is V equals D over T. But we're looking for your time. That means if we actually rearrange it, which is what we do, distance over time, and including this on rule number 4, plug and solve. So we plug in the variables that we have from rule number 1. So we have that, I made a little mistake, D over V. So our we're actually looking for the distance. We're not looking for the time. See, that's what we got. So your distance is going to equal to your V times your T, which is going to equal to your 40 miles per hour multiplied by your 6 hours. Now, looking at this, your hours cancel out. So what you're going to have left? You're going to have miles left. So you know that this is going to be a unit of a distance. So you know you're on the right track. 40 times 6, that's going to be 240. So your distance that you're looking for is going to equal to 240 miles. Let me go ahead and D on this one. So your distance is going to equal to 240 miles. Let's do another example, shall we? Let me go ahead and save this. Let's say, how long does it take to travel 100 miles at 40 miles per hour? So this time we got a distance of 100 miles. So that's going to be your 100 miles. So there's going to be your distance, and this is going to be 40 miles per hour. That's going to be your velocity. So going back over here, and there's going to be example, time example. And this is going to be example time. Now, for rule number 1, our information, you got 100 miles, so your distance is 100 miles. And your velocity is 40 miles per hour. Actually, let me go ahead and write down the word miles per hour. And we're looking for this time. We're like, how long does it take? So that means we're looking for your time. That means your time is your double question mark. Write down number 3. We write down the equation. The equation is V equals D over T, which we're looking for the time. So that means your T is going to equal D over V, which is going to equal to your 100 miles divided by 40 miles per hour. Actually, let me go ahead and put this down instead of just putting it up per hour, which is going to go up on top over here. One of the zeros cancel out, so you get 10 divided by 4. So what that will be 2.5 divided by 1. So this means that your velocity, that the time that we're looking for is going to equal to 2.5. And again, your miles is going to cancel out, and what you're going to have left is hours, which again, our unit complemented our variable what we're looking for in the question. That means we're on the right track. That means we have the correct answer. So this is how you use my 4 fantastic rules. Let's do one more example, shall we? So you are standing 100 meters north of your car when an alligator appears to 20 meters north of you. and beacon runs towards you at 8 meters per second. At the same moment, you start to run at 5 meters per second. Will you reach a car before the alligator reaches you? All right. Well, let's look. In this example, you have two variables. You got a person, which is you, and then you got an alligator. So let me go ahead and do the example 2.2. So you got an alligator, and again, I am really a bad drawer, so I'm just gonna go ahead and draw the best alligator I can. And here's his eye over here, here's his teeth, and this is his little feet over here. And you're over here, and here is the car. You run away to safety. And actually, yeah, you can make this into a truck car. There you go. Now, you are setting 100 meters north of your car. So the distance between your car and over here is 100 meters. And the alligator is 20 meters north of you. So your alligator and distance between you is 20 meters. That means that the total distance for both from the car to the alligator is going to be 120 meters. So I'm just going to say one is the man, and I'm going to call that two is the alligator. So your D1, your 100 meters, that's going to be the distance. I'm going to call the distance from the man to the car, which is going to be D1, is going to be 100 meters. That means your D2, the alligator to the car, is going to be 120 meters. We also got in the question that the alligator is running at 8 meters per second. You're running at 5 meters per second, which is both velocities. So your V1 is going to equal, which is the man, 5 meters per second. Your V2 is going to equal to 8 meters per second. Now, the question is whether the alligator is going to get to you before that car. So it means you're going to need to get the time for the alligator and the time for the man. In this case, having to write down the equation, your V equals D over T, which means your T equals D over V, which means that your T1 is going to equal to D1 over V1, which is going to be 100 meters divided by 5 meters per second. Your meters cancel with meters, so what you're going to get? 100 divided by 5, which is going to be 20 seconds. The alligator is going to be D2. Oh, actually, let me go ahead and get a different color on that. D2 equals D2 over V2, which is going to be your 120 divided by 8 meters per second. Again, your meters cancel out. So what you're going to have is what? 15 seconds. So, which means that you're dead. You're dead. Let's go ahead and check our answer. Which basically that's what we got right now. 20 seconds and 15 seconds, that means you are dead. Awesome. Now, like we said, there are two types of physical quantities. You got scalar quantities and you got vector quantities. Scalar quantities have a magnitude only. For instance, time is a scalar quantity. If I ask you what time it is and you say it's 5:43 p.m., if I take you and put you upside down and ask you what time it is, the time is still going to be the same, 5:43 p.m. Your speed is the same thing. When I call you, it doesn't matter what direction you are going. You can be like, oh, the speed I'm going at, I don't know, 54 miles per hour. That's your instantaneous speed. Now, your vector quantity have both magnitude and direction, such as velocity or acceleration or force, where the direction matters. So that's again the difference between speed and velocity. The speed direction does not matter. That's the same speed. When you talk about velocity, we're talking about average velocity. The direction does matter. So we're talking about vectors, if it's represented by an arrowhead line whose length is proportional to the magnitude of some quantity and whose direction is that of that quantity. Now let's go ahead and look at this vector component that we have, video.
We'll use this animated vector.
Now, when you're talking about a vector, you're talking about it's a resultant from two things, your y and your x component. So this line over here, that's the beginning, that's your y, your x component. Your other line that's going through the y, that's your y component. Now, each one would have an x and a y axis. So coming on here. So let's say you get a vector this is the direction that it's going. Well, this one is a resultant of your y component and your x component. And this is going to be your angle theta. So when you talk about your sine of the angle theta, you're talking about your y-axis divided by hypotenuse. Your cosine theta is going to be your x-axis. Actually, let me get a different color of that. Is your x over h, your hypotenuse. So this one, so your cosine is your x over hypotenuse. So this is, if this was, let's say this is your, no, we call it your v vector. So this is going to be your v of y. And right now over here, which is this one over here, that's going to be your v of x. Now, when you have two vectors, you add it head to toe. Let's go ahead and watch this video over here.
The sum of the two vectors changes if vector B is equal to the orientations.
So basically, to add the vector, when you have two vectors, you add head to tail, and you get the resultant vector that we have. And again, this resultant vector is a product of your x-axis and your x-axis vector. Come back over here. The resultant vector, is going to be a product of your x-axis and your y-axis vector. Now, so let's say you have a vector like this one. So you got a vector v, that's a product of your x and your y component. Now, in order to find the magnitude of v, this we're using the Pythagorean theorem, which is going to be square root of your x component square plus your y component square. So let's say in an example, says using Pythagorean theorem to find the displacement of a car that goes north for 5 kilometers and east for 3 kilometers. So this is example 2.3. So you get a car that goes up at 5 kilometers, and then it goes this way at 3 kilometers. Well, again, using the head-to-tail method, head-to-tail, head-to-tail, that means here's the resultant vector. Sorry, I don't know. All right. Okay. Yeah. This is going to be our 25 plus 9, so it's going to be square root of 34, which if we solve it, we should get close to 36, 696, so it should be 5.83 kilometers. Awesome. Now, we talked about velocity. We talked about distance. We talked about time. So if you are, let's say, in your car over here, and you are going and let's say you're at a different speed, right over here, you're at speed 1, and you became at speed 2. How did you get there? Well, I don't know about you, but when I'm in my car, and when I go to a different speed, what I do, I press the acceleration button, the acceleration pad, which releases more acceleration to the gas, and you accelerate more. Or you press the brakes, which you deaccelerate. So we're talking about something new called acceleration. So let me go ahead. Acceleration. And we can define the acceleration as is a change of the velocity. Let me go ahead. Change in the rate of velocity. Which means, we're going to give you acceleration at letter A. So your acceleration means you're changing from a final velocity, from initial to final velocity over a period of time. So your A is going to equal to your VF minus VI over T. So your VF is going to be your final velocity that you end up with. VI, that's going to be your initial velocity that you start up with. And again, your T over here, that's going to be your time, where your A is your acceleration. So your acceleration is your final minus your initial over your time. So let's say you have, and let's go ahead, open up our little thing over here. So you got a car that accelerates from 15 meters per second to 25 meters per second in 20 seconds. What is the acceleration? Again, using my 4 rules that we've been using. So this is going to be example 2.4. So your car accelerates from 15 meters per second, so VI is 15 meters per second. You final at 25 meters per second in 20 seconds. And you're looking for your acceleration. That means your acceleration, which is your VF minus your VI over your T, which is going to be your 25 minus 15 divided by 20. So we should get 10 divided by 20 meters per second. Divided by seconds. So what we should get 1/2 meters per second squared. And that brings us to your unit for your acceleration. Is going to be your distance over time squared, which is in this case is your meters per second squared. So your acceleration, again, is defined as VF minus VI over T. That means if you solve for your final velocity, what you're gonna get? You're gonna be your AFT plus your initial velocity. If you solve for the initial velocity, it'd be VF minus A of T. Now, having defined that A equals your VF minus VI over T. Again, where your VF is your final velocity, VI is your initial velocity. And having defined VF equals V naught plus A of T. Now, taking the velocity that we have, let's say your average velocity, actually, before we talk about average, let's say the velocity is actually the displacement of your final position divided by your final time. Well, your initial position when you start is going to be 0. Start from 0. Same thing with your initial time is going to be 0, which means this is going to go to 0 and this little fella is going to 0. Which means that your velocity is going to equal to your x over t, which means that your distance x equals your velocity times your time. Now, your average velocity is going to equal to what? Is going to equal to whatever final speed plus whatever initial speed divided by 2. It's your average, your initial plus your final divided by 2 when you have an average of 2, which you can actually rewrite as V 1/2 V final plus V initial. And we define your X as, actually, let me get a different color on this, as V over T. Well, now which V? When you go, you don't go the same, when you go the distance, you don't go the same velocity. It's different velocity. So this is going to be your average velocity. So basically, which is this little fellow over here, that's going to be your average velocity. So your average velocity plugging that back in where your x equals, I mean, we need a different color. Times your time, having to substitute your average velocity in. You're gonna get your 1/2 V naught plus VI, or V final plus VI times your T. This means that you have your X equals your 1/2 V final plus your V initial times T. And your final velocity that we defined is going to be your initial velocity plus A of T. Having both of these in, that means your X is going to equal to 1/2, substituting these in, what you're going to get, V initial plus A of T times T, which is going to equal to 1/2, 2 times V, the initial velocity, plus A of T times your T, which means this is going to equal to your 1/2 times 2 VIT plus your 1/2 A times T times T. Well, in this case, your 1/2 is going to cancel out, and these two are going to become square. Let me go ahead and do it over here. That means your X out is going to equal to your V naught T plus AT squared over 2. Now, what is X? We actually define X as a fancy word for distance. So usually your X is what it is distance. And we actually give distance a variable D. So, which means that your D is going to equal to your V naught T plus your AT squared over 2. And that's our distance equation formula. Now, starting in from initial position, let me go ahead and write this down. Your D equals your V naught T plus your AT squared over 2. Now, starting from your initial position, that means your initial velocity would go to 0. So that means when you start from rest, this goes to 0 when starting from rest. So that means your distance is going to equal to AT squared over 2 when starting from rest. And that brings us to our acceleration that we've been talking about. So the acceleration of an object is the rate of change in its velocity and its effective quantity. Now, for a straight line motion, the average acceleration is the rate of change of speed, where A is the acceleration, T is the time, VF is the final speed, and VI is the initial speed. We rated this example where we had a car accelerate from 15 meters per second to 25 meters per second in 20 seconds. We found out that the acceleration was 0.5 meters per second squared. And notice it's meters per second squared because it's distance over time squared. That's your unit for acceleration. We also took the acceleration, which equals VF minus VI over T. We solved it for your final velocity. Now, so some books goes from 1 to 2. Some books use VI for initial and VF for final. It's both the same thing. So let's go ahead and do this example. A car whose brakes can produce an acceleration of minus 6 meters per second squared is traveling at 30 meters per second when its brakes are applied. What is the car speed 2 seconds later? And what is the total time for the car needed to stop? Okay, example 2.5. Let's go ahead and say this. Our first piece of information is your acceleration, which is minus 6 meters per second squared. our second piece of information. And this one is you're traveling at 30 meters per second. So your velocity is, your initial velocity is 30 meters per second. And you are going to do it in, what is the car speed? 2 seconds later. So your part A, your time is 2 seconds. And you're looking for your final speed. Now we have an acceleration having to use your A equals VF minus VI over T. We're looking for VF, which is going to be your final velocity, which is your VI plus A of T, which is going to equal to our VI, which is going to be 30 plus minus 6 for the acceleration times 2 for the time. So we get 30 minus 12, which is 18 meters per second. The second part is asking for the total time needed for the car to stop. Now, that's part A. Part B, when the car stops, your final velocity is going to equal to 0, where your final velocity is going to equal to your V1 plus A of T, which is again is going to equal to 0. That means your time needed that you're going to need is going to equal to minus V1 over your acceleration, which is going to equal to minus 30 divided by minus 6 from our information. Negative goes with a negative, becomes a positive. 30 divided by 6 is 5 seconds. And again, if we actually wrote the units over here, this is going to be meters per second times meters per second square. Your meters cancel out, and when the seconds cancel out, this goes back up and you get seconds. So, which is the correct unit for our answer. Now, yep, we are correct. Now, if we know the initial velocity, the final velocity, and the acceleration, then we can determine how far an object travels in a given point of time. And we actually derive this equation where we get your distance is going to equal to your V1t plus 1/2 AT squared. Starting from rest, where V1 is going to equal 0, that means your distance is going to equal to 1/2 AT squared. Now, let's go ahead and we look at this next video that we have.
It's a nearly frictionless air trap, with the guide floating on an air cushion and demonstrating turn the track by placing a 1 centimeter high shoe under my hand. That is not the track. What do you say about the magnitude
Of the dots going in. Is it going at a constant? Is the glider going in a constant rate? Is it going at a constant rate, increasing rate, decreasing rate, and can't tell? Now, remember, they added an incline. So let's go ahead and see the answer. Go ahead and lock in your answer.
that is velocity increases with time? 7.
Notice the higher it is, the more spacing between the dots go with the time increases, which means it increases the acceleration.
This shows
Notice the biggest angle of tilt has more space between the dot. That means it accelerates faster as time it goes. Now, how far did the car in example 2.5 travel before coming to a complete stop? And again, let me go ahead. So we had, I guess let's do this part C. We had the velocity, the time at 5 seconds, the acceleration at -6 meters per second square, and we had the velocity at 30 meters per second. And we're looking this time for your distance, which your distance that we had included is VIT plus AT squared over 2. So this is going to equal to your 30 times your 5 plus your -6 times your 5 squared, which is going to be 25 divided by 2. So you should get 150 minus 75, and your answer would be 75 meters. So your distance traveled is going to be 75 meters. Now, when you drop, when something goes through the air and should go in a free fall, we have a case of something called gravity. Now, one of the first people that acknowledged gravity is Galileo Galilei, which he performed his experiments, and he got actually in trouble with the Catholic Church. Basically, what he did, he went down to the Pisa Bridge, and let me go ahead and draw the Pisa Bridge. Actually, that's a little tilted too much. It's more like, here's your Pisa Bridge. He goes over here and he drops 2 balls, a small ball and a big ball. Now, when dropping them up in the same time, he found out that the higher the stone is when it's dropped, the larger the speed of the stone when it hits the ground. He also realized that both of them hit the ground at the same time. That means you realize that the acceleration acting on both stones are constant. That means the velocity is directly proportional to the time that the object has been falling. So he found that the higher the stone is, when they drop, the larger the speed of the stone, and the acceleration acting on the stone is constant. That means the speed of the falling object depends on the time, not the object's mass. Again, for both balls, when they came down, they both arrived at the same time down here. Now, this constant acceleration that we got is called gravity. And we is measured at 9.8 meters per second square. And most of the time you see it given as the little g. So the acceleration of gravity for objects in free fall is 9.8 meters per second square. Now it's also equivalent to 980 centimeters per second square or 32 foot per second square, but mainly we're going to be using the 9.8 meters per second square. So when we're talking about your distance, which is your VIT plus AT squared over 2. If you're coming over here, let's say you're standing right over here on top of the building, and you drop a stone. You drop an object going down here. Well, this distance that is going is called what? This distance is actually called height. So we can actually define this as your height. Now, the stone has a initial velocity. The initial velocity for it is going to equal to 0. So in this case, your height, which is your VIT plus AT squared over 2, is going to equal, this is going to go to 0. So basically, you're getting a 0 plus. Now, what is making this go down? Again, we define this acceleration as gravity. So this acceleration over here that we have is going to equal to G. Let me get a different color so you will see it better. This acceleration is going to equal to G, which is going to equal 9.8 meters per second squared. So you can actually substitute this for G times your time squared divided by 2. That means your height is going to equal to GT squared over 2. So when we're talking about free fall, we're talking about your height is going to equal to gravity times the time squared divided by 2. And again, let me go ahead and write this down. GT squared over 2. G, that's gravity, which is 9.8 meters per second squared. T, that's your time. And H, that's your height. So when we're talking about an example over here, example 2.8, a stone drop from a bridge strikes the water 2.2 seconds later. How high is the bridge above the water? Okay, so we got your 2.2 seconds. So this is going to be example 2.8. Your time is 2.2 seconds. And you're looking for your height. And you know your height is going to equal to GT squared over 2, which is going to equal to 9.8 times 2.2 squared divided by 2. And so for this, you should get close to 24 meters. And again, notice it's meters because it's a unit of distance. And that's what height is. Height is another fancy word for distance. Right. Okay, so let's do another example, shall we? An apple is dropped from a window 20 meters above the ground. How long does it take it to reach the ground? And what's the final speed? So this is going to be example 2.9. So your height is 20 meters. For part A, how long does it take the apple to reach the ground? So we're looking for your time. And we're dropping the ball. So basically, we're writing down the equation. H equals GT squared over 2. Again, we're looking for the time. So solving for your time, what you're going to get? You're going to have your 2H over G, square root of that. So it'll be 2 times 20 divided by 9.8. And you should get close to, let's say this 10, 20 divided by 10. It'd be 4, so it'd be close to, I would say 4 seconds. Now, what was the final speed? B, your final speed is going to equal to, you're looking for your final speed. You know from your acceleration that your final minus your initial divided by your time. Again, your initial is going to be 0. That means your final speed is going to equal to your acceleration times your time, and your acceleration is going to be your gravity times your time, which is going to be 9.8 times 2. So you should get 19.8 meters per second. Wonderful. Now, An object thrown horizontally has a vertical acceleration of 9.8 meters per second square and a constant horizontal velocity. Its trajectory is a curved path. In the absence of resistance, the curve is a parabola. So when you're throwing an object, again, we talked about this, the resultant of that object is actually a result from the horizontal vertical and your x vertical. So if you have an object, let's say you got an object right now over here that is going this way, and let's say you get it, I don't know, acceleration A, this is going to be an equivalent of your y component and your x component, which again, this is your resultant, this is your vertical and your horizontal. So let's go ahead and watch the next video.
How is the vertical motion of a polygon affected by its horizontal motion? We use this device to find out. If the ball is moved up and back, it's explode. Same time we find other horizontal. Which will strike the ground?
Which one will strike the ground first? So if you hit them both, one that's pushing to forward and the other one is going down, which one will start the ball for the ground first? Would it be the ball that drops straight down, the one that goes sideways, both will go at the same time, or any of the above? Go ahead and guess your answer. And hence you got your gravity accelerates on both of them at the same time also. Now, this object that throws back, though the object thrown upward falls back at an earth that accelerates 9.8 meters per second square and returns to its starting point with the same speed as it's thrown. Okay. Now, having to throw, which angle with actually goes the furthest distance? Let's go ahead and watch this over here. Okay, here's a video, it's already loaded. So what angle do you think the ball should be launched to for it before striking the distance? When you throw an object, how can you throw the object the furthest distance? Would it be 15, 30, 45, or 60? Those are the choices. Go ahead and lock in your answer. Let's go ahead and look.
This spring-loaded gun can launch small root balls at different angles with the same speed.
Which angle do you think? That's 15, 30, 45, 60. According to this one, 45 would be the maximum angle for the maximum distance. Now, let's go ahead and look at the next video. Let's talk about a little bit about friction.
Stops really. Stops sliding. Slows down only gradually.
All right, so in real life, friction forces are always present. The direction of the friction force always opposes the motion. When you walk, you're going straight, your friction goes opposite of you. That way you can walk in the direction that you want. Friction is bad sometimes because it dissipates energy, but it's good because it allows you again to run, walk, stop, etc. Now let's go ahead and look at the next one.
Static
All right. And the next one. The board. So basically, he put the board on the side and he's moving. Would it be using more or less force? Let me go ahead and see the question. Will the force be required more, less, or the same, or you can't tell? What do you think? The force remains about the same. It doesn't. For example, when you tow your car, whether you tow it on the side or whether you tow it on upside down, you're still going to be using the same amount of force needed.
This incline has 4 different surface materials.
See, if you look at it on the side view, your Teflon is this least amount of surface that has friction. So it's at 18 degrees, followed by your wood at 22 degrees. And then you follow by your sandpaper at 25 degrees. And then rubber is like glue. It's going to be about almost 40 degrees or 50 degrees in order to go down. Wonderful. So force of sliding friction is much less than the force of static friction. When you move an object, it's faster to go in. Now, friction between two solids does not depend on the surface area in contact. Now, it can happen between any two surfaces that are not solids, two surfaces that are not solids, for example, liquids and gases and air, right? Now, one of the things that's going to affect it is called air resistance. So air resistance prevents a falling object from reaching the full speed produced by the acceleration of the gravity. Now, air resistance increases with the speed of the moving object. So let's go ahead and see the next video. So why do you think light and heavy objects fall differently? Because objects in the fall faster in the air than vacuum, and the air lighter objects fall faster than heavier objects. All objects fall at the same rate in the air, and all objects fall at the same rate in vacuum. Okay, well, let's go ahead and look at the answer.
We will use this pair of tubes containing metal.
Notice that the paper and the coin are both falling at the same rate because we had a vacuum. When we talk about vacuum, we took the air out. So there is no air resistance. So, and I'm going to skip ahead a little bit. I'm going to go back. So in the absence of air resistance, it found that all bodies at the same location above the Earth fall vertically at the same acceleration. If the distance of the fall is small compared to the radius of the Earth, and the acceleration remains essentially constant throughout the descent. Now, the ideal motion, like we just talked about, is called free fall, and the acceleration of the free falling object is called the acceleration due to gravity, which is 9.8 meters per second squared. And this is the actual video that we actually just saw a little while ago. All right. Now, so what we did, we talked about the terminal velocity, which is the maximum speed a falling object obtains when the force due downward acceleration of the gravity is balanced by the upward force of the air resistance. Now, the terminal speed of any object depends on the object's size, shape, and mass. And that's really when we talk about kinematics and dynamics. Kinematics is deals with the concepts that are needed to describe motion. Dynamics deals with the effect that forces have on motion. Now, together, kinematics and dynamics, they form a branch of physics that we're actually talking about called mechanics. Now, in the mechanics, one of the things we talked about is your displacement. So, your displacement usually goes in. We used x for your displacement d. So, your displacement is your change in or your distance, which is your displacement, is your change in your distance. So let me go ahead. Where we define x naught as your initial position, your final as your x final as your final position, your delta x, which is going to be your displacement. Write it down better. Which is your delta x, which is going to be your x final minus your x initial. And they're both as vectors. So, for instance, if your x initial was 2 and your x final was 7, that means your delta x, it'd be 7 minus 2, which is going to be 5 meters. Okay, let's say if your initial x was 7 and your final was 2, it'd be 2 minus 7, so your delta x would be minus 5 meters. And again, the negative tells you the direction that it is going. So let me go ahead over here. So let's say your x initial again was 2 meters and your x final is 7 meters. That means your delta x is going to equal to 7 minus 2, which is 5 meters positive. It's positive, that means you're going this way at delta x is going to equal to 5 meters. Another one, let's say your x, the next one was going to be your x initial as 7 meters and your x final is 2 meters. That means your delta x is going to equal to your 2 minus 7, which is going to be minus 5 meters. That means your delta x is going to be going this way at 5 minus 5 meters. Again, the negative just is the direction that you are going. There's another example. Let's say your initial was at minus 2 meters and your final was at 5 meters. That means your delta x is going to equal to your 5 minus your minus 2, final minus initial, which is going to equal to 7 meters. So your delta x will be going this way at 7 meters. Put it that way. Wonderful. So your average, and that's what we just did. So the average speed is the distance traveled divided by the time required to cover that distance. Now your average speed, again, is distance divided by your time, which is your meters per second. And we just saw that. So how far does a jogger run in 1.5 hours at speed 2.2 meters per second? So let's say this is example 1. You got your distance at 1.5 hours. And your velocity at 2.22 meters per second. I'm sorry, that's your time. You're looking for your distance. That means your distance is going to be t, which is going to be your 2.22 times your 1.5 hours, which which is going to equal to it'd be 3.33. Actually, hold up. Our velocity is meters per second, so we need to change this into seconds. So this is going to equal to 1.5 hours, and for each 1 hour is 60 minutes. And for each 1 minute is 60 seconds. This cancel with this and this cancel with this, and you should get 36 times 1.5 is 5,400 seconds. That means this is going to be times 5,400, and you should get 12,000 meters. Yep, that's correct. Now, the average velocity is the displacement divided by the elapsed time. And that's what we just saw, which is going to be your average velocity, your x minus x naught over t minus t naught, which is your delta x over your delta t. So here's another example that we can actually use. Our first piece of information. So Andy Green, the car thrust is he set the world record of 340.1 meters, 341.1 meters per second, 1997. To establish such a record, the driver makes 2 runs through the course, one in each direction, to nullify wind effects from the data determine the average velocity of each run. So on your first one, your time is 4.74, where the delta x is 1609. So go ahead, example 2. So your delta x So this one from our diagram, your delta x equals 1609 meters. And your time equals 4.7 seconds, 74 seconds. Which means that the average velocity, which is your change of x over change of t, is gonna equal your 1609 divided by 4.74. And if you dug it in, let me go ahead and plug in the calculator. It'd be 339.5 meters per second. On our second one, the delta x is going in the negative direction, so we minus 1609 at 4.695. So your delta x, let me go ahead and get a different color. And this one will be minus 1609 meters. At t equals 4.695 seconds. That means your average velocity, which is going to be your delta x over your delta t, is going to be minus 1609 divided by 4.695. So you should get 342.7 meters. And that's what we actually worked on since the beginning of the course. So in terms of velocity, it gets how fast a car moves and direction of the motion each instant of time. Now, the notion of acceleration emerges when a change of velocity is combined with the time during the changes, which we actually saw, which is going to be your final velocity minus your initial velocity divided by final time minus your initial time, which is delta v over delta t. So for example, if we have your V naught is 0, your final is 260 going at 29 seconds. So this is example 3, which we said V initial is 0 meters per second, along with T initial is 0 hours or 0 seconds. Wouldn't matter because seconds anyway, it's 0. Your final velocity, which was 260 kilometers per hour. And T final is 29 seconds. Which your acceleration is going to equal to. Now you can change this to seconds, to hours to complement this one. So 1 hour is 60 seconds, is 60 minutes. 1 minute is 60 seconds. Your seconds go away, your minutes go away. Should be 29 divided by 36. So this is going to equal to 0.008 hours. That means your acceleration is going to equal to your 260 divided minus 0 divided by 0.008 minus 0. So that's going to be 260 divided by I got 32,500 kilometers per hour. Awesome. All right, now. So we said that the initial position is 0. Your initial time is 0. Plug in the average velocity. We actually defined this earlier at x equals 1/2 v naught plus vt. When we actually also took the acceleration equation and we solved it for the final velocity, which equals your initial velocity plus aft. That brings us to the 5 kinematic variables. And let me go ahead and write them down. Your 5 kinematic variables. Number 1, which is your displacement, which is define that as the x. Your acceleration, which is your a. Number 3, your final velocity, which is your v of f. Number 4, your initial velocity, which is your v of I. And last but not least is your time, which is we gave it a variable t. Which brings us to the kinematics equation. Just change color on me. Your first one will be your v final equals your v initial plus aft. Your v initial is going to equal your v final minus aft. Your x equals 1/2 v final plus v initial times t. Your v final square is going to equal v initial square plus 2a of x. And the last one, your x equals your v naught of t plus your at squared over 2. And we define each one of those equations. So let's do this little example for instance. Let's go ahead and open up. You get a speedboat that has a constant acceleration of 2.2 meters per second squared. Has a velocity at 6 meters per second. Find the boat's displacement after 8 seconds. So let's do this example over here, shall we? So your acceleration is 2 meters per second squared. Your initial velocity is 6 meters per second, where your displacement is 8 seconds. And when the distance. Okay, having used one of these, so which one would you use? We have the acceleration, initial time, and your x. So that means we can use this equation over here. That means we're using the equation. Let me go ahead. X equals v naught t plus at squared over 2. This is going to equal to 6 times 8 plus 1/2 times 2. T squared is 8 squared. So 8 squared times 2, these two canceled out. 6 times 8, so what you're going to get, you should get 110 meters. All right, let's do another example. Let's do example 8. Spacecraft traveling at velocity of 3250 meters. So our 3250, that's going to be our example 8. Your initial velocity is 3250 meters per second, where and it slows down with acceleration magnitude of 10 meters per second square. So your acceleration is minus 10 meters per second square. And your distance is at 2115 kilometers per hour. So your distance x is at 215 kilometers. And we're looking for your final speed. Well, the only one that we don't have is your time. So let me actually get to the color. So you don't have a time, which means going back to these equations, we can use the time equations. We can use this one, or that one, or that one. So that means we use this equation over here, VF squared equals VI squared plus 2AD. So that means the equation that we're using is V final square equals V initial square plus 2A times X, which means solving for your final velocity is going to equal to the square root of V initial square plus 2AX, which is going to equal to square root of your 3250 square plus 2 times minus 10 times your distance, which is 215 kilometer K. And you should get, actually, let me just go ahead and solve it all. (2,500 meters per second). Let's go ahead and check our work. Yep, 2,500 meters per second. That's correct. Let's do one more example, shall we? We already talked about this. So a stone is dropping from the top of the tall building after 3 seconds of free fall. What is the displacement of the stone? So you got initial velocity 0. Going in 3 seconds, you need the displacement, which is your x. So in this case, let me go ahead and write down the information. This is going to be example 10. So your V naught is 0. Your initial velocity is 0 meters per second. At a 3 seconds, so your t equals 3 seconds. And it's falling down. So at the free fall, so your acceleration, which is your gravity, is going to be minus 9.8 meters per second square. And you are looking for your displacement, which is your y or your x. Now, notice that we do not have an initial velocity, v of I. Going back over here, that means you cannot use this one, you cannot use that one, you cannot use this one, you cannot use that one. That means you can use the final one, which is, we're using x, but we're going horizontal, so we can say it's a y. So in this case, your from over here, your y is going to be not vi of t plus 1/2 at squared over 2, or plus at squared over 2, I'd say it. Which this is gonna go to 0, because again, this is gonna equal to 0. So your y is gonna equal to your gt squared over 2. In this case, it would be 9.8, and you can actually go as a negative times your time squared, which is 9 divided by 2, and you should get 44.1 meters. And when you say negative 0.4, that means you are going this way at 44.1 meters. That's where the negative goes in. And that should conclude chapter 2 for Cutnell Physics 1 with algebra. Let me go ahead. All right, if you have any questions, please email me at abunaemeh@gmail.com, or you can call me at 256-348-1480. Thank you for watching.